Topic today, we're going to talk about reversible reactions and the concept of equilibrium. This is a big part of this unit. So first up, what is a reversible reaction? Well, if you think about a typical chemical reaction, we tend to write these as reactants forming products. So what's happening on the molecular level? What's happening to the atoms? If we think about that chemical reaction, we've got our reactants that collide with each other, and in doing so, if they have enough energy and collided in the right orientation, they form products. But is there anything that prevents them from going in the reverse direction? Is there any reason they can't collide again and form the reactants? Let's take a look at this. So up to this point, you may have just naturally assumed that chemical reactions always and only progressed in one direction, the forward direction in which you wrote them. But this doesn't have to be true. Some reactions are reversible. And if a reaction is reversible, that means that the change from reactants to products and the change from products to reactants can occur at the same time. So let's take an example. We could have a reaction in which SO2 and O2 collide and react to form SO3, and that would be this forward written reaction. But there's really no reason that SO3 molecules can't collide and split apart to go the other way, to make SO2 and O2. The first reaction is a forward reaction. The second reaction is the reverse of that reaction. And we don't need to write these out twice. We can combine them into one equation and use this double two-way arrow. It shows us that the reverse reaction takes place, or that the forward reaction takes place, as well as the reverse reaction. So these arrows, these are used for reversible reactions. It's telling us that as SO2 and O2 are colliding together to make SO3, at that same time, SO3 molecules are colliding together to make more SO2 and O2. Now let's look at a visual representation of this. Over here, well, in all of these boxes, we have a mixture of SO2, O2, and SO3 molecules. Now in this one, we have just SO2 and O2. So as these molecules collide, all that is available is SO2 and O2. As they collide, they're going to start producing SO3. We'll jump over here. But as the SO3 starts building up, these are going to collide together as well. And when they collide, they will produce SO2 and O2. So the end result is this middle box. We'll end with a mixture of all three of these substances, because still the SO2 and the O2 will be combining to make more SO3. But as they do that, SO3 and SO3 will be colliding to split back apart and make more SO2 and O2. So since these reactions happen at the same rate, the forward reaction happens with the production of SO3, and the reverse reaction happens with the decomposition of SO3, we end with an equilibrium mixture of all the substances. When the rate of the forward and the reverse reactions equal out, we've reached a state of balance known as chemical equilibrium. Let me go back to that picture for 1 second to talk about this. So we've reached what's called dynamic equilibrium. Reaction is still happening. We still have SO2 and O2 making SO3. But since at the same time and at the same rate we have SO3 decomposing to make SO2 and O2, we wouldn't see any change in the total number of any of these substances. If two of these and one of these combine to make this product, then at the exact same time, two of this product are decomposing to make more reactant. So individual molecules can still be reacting, but we're not seeing an overall change in the total number of any of these substances at equilibrium. The rate of this reaction and the rate of this reaction, the forward and the reverse, have equaled out. So we are in a state of chemical equilibrium. Now we can approach this state from either side of the reaction. To give you an example, on this side, say we started with a mixture of SO2 and O2. Over here we've graphed concentration. So we start a reaction with a mixture of these two reactants, but 0 SO3. Notice that this line starts at 0. Now, you can watch this reaction progress with time. Initially, the amount of SO2 and O2 decreases very rapidly. Remember our reaction rates from the previous lessons. We've got a pretty fast initial decrease here in the concentration of our reactants. And likewise, we've got a fairly rapid increase in our product initially. Because we had all reactant, it's going to start forming product very quickly. But now as we start to use up that initial amount of reactant, we have less reactant molecules available, and so our collisions slow down and the rate of the reaction slows down. Similarly, the rate at which we're producing SO3 is slowing down here. And we reach a point where the concentration of these substances is no longer changing. We have a slope of 0 after this point. Look at SO2. We started with a lot of it. We started using some up in reaction, so it was decreasing, but the reaction was slowing down as a result. And at some point, we have a constant concentration of SO2. Because at this point, we have SO3 decomposing at the same rate that it's being produced. So initially, it's being produced very quickly, really growing in concentration, but then again the reaction starts to slow down as more of it's produced. Some of it's going to start decomposing to make more SO2 and O2. And then we reach this point here where all three stop changing in concentration. So we've reached an equilibrium level of these three, an ideal ratio between them where they are constant. If more SO3, if a molecule of SO3 decomposes to make more SO2 and O2, then at the same time, at the same rate, some SO2 and O2 are going to collide to make more SO3, so that these lines remain level and constant. Now this was the situation, remember, when we started with SO2 and O2 and 0 SO3. But we would have gotten the exact same thing if we instead started with a large amount of SO3, so a large amount of product, and 0 reactant. Because now, initially, we have all SO3, so some of it's going to start decomposing to make more SO2 and O2. And as it decomposes, we have less of it available. That decomposition slows down until we reach the same concentration level as before. So it didn't matter if we started on the product side or the reactant side. We reach the same equilibrium levels of these three substances. Here's another way to think about that condition of equilibrium. So if you think about going to the mall, which we'll eventually be able to do again one day, when the store opens, nobody is currently inside the store, no customers. And so if you were to measure the amount of people going in versus the amount of people coming out, you'd see that there are way more people going in. The reaction, as you will, has just started to occur. We have only reactant right now, only people outside headed into the store. But if you give it some time, now the first people into the store are done, they're coming out, people late to get there are going in. Eventually we will reach a state where there are the same amount of customers going in as there are coming out. So if you picture inside this store, say 100 people went in the first hour. So we had 100 in. But then as some started to come out and more started to go in, we reach a time where there is always 50 people in the store. Not necessarily the same people. One shopper decides they're done and they leave. They're replaced with a new shopper who just arrived. So the people in the store are changing, but there's always 50 people in this store in equilibrium. So by definition, at chemical equilibrium, both the forward and the reverse reactions continue, but since their rates are equal, there is no net change in the concentration of any of the components or substances. Now, an important distinction here. The rates are what is equal. The rate of the forward reaction equals the rate of the reverse reaction. This doesn't necessarily mean that the concentration of the components are equal, and in fact, the concentrations normally are not equal. There's a relative amount of each concentration of each reactant and product to each other. This is called the equilibrium position. Like I said, it's like having an ideal ratio of product to reactant. It's not necessarily 50-50. It doesn't have to be, and it usually isn't. We can, in many chemical reactions, produce a lot more product than reactant, but we will still have a set, definite equilibrium ratio between the product and the reactant. So even if, let's see, let me go back to that store picture, sorry. Even if there are 1,000 people outside the store, say, and only 50 people inside, we've still reached equilibrium. We didn't have to get to 500 inside and 500 outside. All that matters is that every time one person comes out of the store, one person goes in. We have a ratio of 50 inside to 1,000 outside, and that's all we have to do to satisfy equilibrium. So the equilibrium position can tell us whether the forward or reverse reaction is more likely to happen, whether it's more favorable. So let's take an example. Let's go back and we have this general equation of the reactant A reacting to produce the product B. If the equilibrium mixture contains just 1% A and 99% B, then we know that the products were favored. The formation of B was favored. The forward reaction was favored. Here that's shown by giving the forward arrow the longer line. This expression here shows that this reaction is product favored. It will reach an equilibrium mixture. It will reach an equilibrium ratio, an equilibrium composition that is 1% A and 99% B, and after that point, no more B will be produced, even though there's still A present. We're at equilibrium even though we're not at 50-50. B was favored, and we produce more of it. Now, in theory, pretty much any reaction can be reversible under the right conditions. In practice, one set of components is typically so favored at equilibrium that the other set can't be detected. So we would consider this to be an irreversible reaction. Doesn't mean it's impossible. Let's say we have a reaction that produces 99% product like before. Doesn't mean we can't go backwards and produce reactant. No, we can. It's just not favored. It's a lot harder. We'd have to input more energy, do it at a higher temperature maybe. It's not going to happen naturally. And so for most practical purposes, we would just consider that reaction irreversible, because under typical conditions, it really favors one side so much. So in that case, if we have a reaction that is so product favored that we can't detect any reactants, we'd say we had a complete reaction or it was irreversible. If we put two reactants together and can't detect any formation of product, we would say that no reaction took place. So let's talk about what would affect this equilibrium position. This brings in a really fun principle. It's called Le Chatelier's principle. Very fun to say. You can pause and do it a few times, feel fancy. And this principle is great because it's fairly intuitive. It talks about stresses that can cause the equilibrium position of a system to shift or change. Now, this was proposed by French chemist Henri Le Chatelier. He proposed his principle in which he said that if a stress is applied to a system that is already in equilibrium, then the system changes in a way to relieve or mitigate that stress. Essentially, if you try and change a system, the system is going to undo it. It's going to try to undo or mitigate that change. A stress that upsets the equilibrium of a chemical system can include a change in the concentration of a reactant or a product, a change in temperature, or a change in pressure. And we're going to talk about these three possibilities. When we say a stress on the system, all we mean is a change to the system that's going to cause it to move one way or another. Let's talk about concentration first. It's probably the easiest to understand. So if you change the amount or the concentration of a reactant or product in a system that was already at equilibrium, you've messed up the equilibrium. Let's say you had a perfect ideal mixture of A and B, then you go and dump more B into your system. You've messed up that ideal ratio, and the system is going to react to minimize the effects of your input. In other words, it had what it wanted. It was happy. It had the mixture of A and B that it liked. You went and added more B, and it's going to say, hey, rude, and change to use up that B to make more A. It's going to try and undo the effect you were putting into it and get back to its happy ideal ratio like it had before. So here's an example. In this equation, we've got the decomposition reaction for carbonic acid when it's put into solution. So this acid is our reactant, and it will decompose to make carbon dioxide and water. And notice this is a very product-favored reaction. We make much more product than reactant. So let's say we've done this. We've let the system sit. It's at equilibrium. We definitely have our 99% product and our 1% reactant. The amount of our reactant that is left is less than 1%. And now we're going to go and we're going to add carbon dioxide into this system. So we had equilibrium, and then we added more carbon dioxide. Now carbon dioxide was a product. So the system was sitting where it wanted to be. We added more on this side, which means the system is going to want to shift this way towards the reactants. We added more product. The system will want to use more of that up, make more reactant until it gets back to its equilibrium ratio. So we've pushed the direction of the reaction towards the reactants. Now when I say we get back to our equilibrium ratio, that doesn't mean we get back to the exact same amount of carbon dioxide we had before. If we had an equilibrium mixture, we had a certain amount of carbon dioxide, we add a bunch more, the system does want to use up what we added, but it wants to do so in a way that will get it back to its equilibrium position. So in equilibrium it had a lot of this and a little of this. As it uses up the carbon dioxide we added, it's going to create more of this reactant. So we will get back to equilibrium, we'll get back to the correct ratio between these two, but in the end we will still have more total moles of carbon dioxide and more total moles of this acid. The ratio is back to being the same, but we have a greater number overall. Now, on the other hand, maybe we could remove carbon dioxide. So again, our system was sitting at equilibrium, and then we pull carbon dioxide out. Now our system, again, doesn't like that. It was at its happy ratio. It was where it wanted to be, and we just took some of its product away. We decreased this side of the reaction. So the system responds by shifting the equilibrium to the right towards the products by reacting more of the acid to make up for the lost CO2. So we will pull the reaction towards the products. We took CO2 away. The system responds by reacting more of the acid to create more of the CO2. It wants to mitigate the change we tried to introduce. Let's talk about one specific example. As people, we have an equilibrium between carbonic acid, carbon dioxide, and water in our blood. Now, during exercise, the concentration of carbon dioxide in our blood increases, which would shift equilibrium in the direction of carbonic acid. Going back to this reaction, exercise increases this. The system would shift towards the reactants, making more carbonic acid. This increased level of CO2, though, would also trigger an increase in our breathing rate. With more breaths per minute, we can start removing CO2 through our lungs. Removing CO2 causes the equilibrium to shift back towards the products to decrease the amount of carbonic acid. So our body uses the concept of equilibrium and Le Chatelier's principle to maintain the right ratio of substances in our blood to keep us healthy. The other factor we talked about was temperature. Now, if we know we can increase the temperature of a reaction, and it will have multiple effects. We already talked about changing temperature to influence the rate. We can also use temperature to influence the equilibrium. And for this, you're going to have to go back to your knowledge of endo and exothermic reactions, because increasing the temperature is going to shift the equilibrium in the direction that absorbs heat. So it's going to favor the endothermic reaction. Let's look at an example. In this reaction, we have a reaction between nitrogen and hydrogen to make ammonia, and this reaction releases heat. We've got heat written as a product here. So we have an exothermic forward reaction. Now, if we add heat, if we increase the temperature, it's like we've added product. And just like before, if we increase over here, the system wants to undo our work, undo our increase. And so it will consume that heat to perform the reverse reaction. So adding heat means we shift the reaction towards the reactants. If we remove heat by cooling the system, then our system responds by producing heat. So we're trying to remove heat. We made this side lower. The system wants to undo our change, and so it will favor the forward reaction to produce and add more of that heat back in. Pressure is just a little bit trickier. It's going to follow the same thought process as before, that if we change the pressure, the system will want to undo our change. And so this comes into play when the reactants or the products are gases, because gases are the most influenced by pressure. So pressure will only cause an equilibrium shift if there is an unequal number of moles of gas on either side of the reaction. So let's look at an example. Here we've got a container that contains an equilibrium mixture of ammonia, hydrogen, and nitrogen. So here we've got our initial equilibrium, and when we push this plunger down, our volume decreases, which means our pressure must be increasing. As a result, the system wants to decrease the pressure, and to do that, it's going to have to decrease the total moles of gas that are there. Because remember, pressure, according to the ideal gas law, depends on your total moles of gas. So let's look at this reaction. We've got nitrogen and hydrogen gas in the reactant side. So over here we've got a total of 4 moles of gas. Over here we've got a total of 2 moles of gas. If we increase the pressure, the system wants to decrease the moles of gas so that it can also be at a lower pressure. So there are fewer moles of gas over here, which means that the system makes more product, it can decrease its pressure. And so when it comes to pressure, you will always be looking at your chemical reaction, and you'll be looking for the side that has fewer moles of gas. Gas is the only thing that's really going to be affected by pressure. The last piece to talk about are catalysts. Now remember, we talked about catalysts in our reaction rates. We know that a catalyst speeds up a reaction. However, when it comes to equilibrium, they will not affect the equilibrium position. They can increase our rate, they can help us get to equilibrium faster, but they will not affect the total number of reactants and products present. So let's do one example here. Here we've got a sample equation. We know it's endothermic because heat is a reactant. And we want to know what effect each of these changes will have on the equilibrium position. So take a second, pause if you want, and write an answer down for each of these stresses, and then we'll talk through the answers. Okay, so let's take a look here. We'll talk through these step by step in one moment. If we add Cl2, we add a product, the system will want to shift towards the reactants to consume that additional Cl2 we added. If we increase pressure, let's see, we've got 1 mole of gas over here, we've got 2 moles of gas over here. The system will want to decrease pressure by decreasing the total moles of gas, so it will shift towards the reactants. If we remove heat, heat's one of our reactants. If we remove it, the system will want to make up for that extra heat. It will shift towards the reactants to produce more heat. If we remove PCl3 as it forms, we're removing product, we're decreasing this side, the system will act to increase that side. It will shift towards the products to make up for that lost PCl3. So the slides are going to walk through that same reasoning. In each case, the equilibrium position is going to shift to a direction to minimize R imposed stress, R change. So when it came to Cl2, we added product, the system will create more reactants. It will shift left. When it came to increasing pressure, the system wants to reduce pressure. It can do that by reducing the total moles of gas available, and will shift left. When it came to heat, heat was a reactant. If we removed it, the system will want to create more heat to make up for that. It will shift left. If we remove PCl3, that was a product. We remove the product, the system will want to increase the product. It will shift right. Alright, one more example for you to look at. Here's another equilibrium reaction. We want to know which direction the equilibrium position will shift with an increase in pressure. So take a second to think through that. So when it comes to pressure, remember all we care about is total moles of gas. So we've got 4 plus 1, 5 moles of gas in our reactants, 2 plus 2, 4 moles of gas in our products. If we increase pressure on our system will want to undo that, so it will shift to the side of the reaction with lower pressure, which means the side with fewer moles of gas, which happens to be our product side. Our equilibrium shifts to the right.